Salutations, mini mathematicians! We are going to be talking about something so cool today. It is about solving systems. Now that you are a master at solving systems of two equations with two unknowns, either graphically with substitution or elimination, we're going to solve a system with three unknowns. I know, magic, wild, real math. And this is going to get you ready. Next year in math, you're going to be solving systems with even more variables than three, and you're going to use something called a matrix. I know, so fun. Okay, so what are we doing? Systems of linear equations in three variables, 4.2c. We're going to use elimination or substitution or like a combo of them to use all three equations in the system to create two equations, the same two unknowns, because you know how to solve that. Then continue solving the system, and you're going to write your answer as an order triple x, y, z. Still alphabetical order. Well, let's talk about what we know. So you're very comfortable plotting in the xy plane, which is also called the Cartesian plane. So in the xy plane, we are limited to our dimensions. So 0 dimensions is a point, 1 dimensions is a line. There's only length, right? There's only one dimension. 2 dimensions is like we can graph like a square or a triangle, so there's length and width. But we can only graph things with area. We can't get to volume because volume is 3 dimensions and we live in a 3-dimensional world. So that's when we need the XYZ plane. So here we can graph 3 dimensions, length, width, and depth. Don't worry about how to graph in the XYZ plane. It will not be part of your education this year with me. But I just wanted to give you an idea of what this would look like. Awesome, let's get started. Okay, 4.2c, systems of linear equations in three variables. A solution of an equation in three variables, such as x plus 2y minus 4z equals 9, is an order triple x, y, z of real number values of the variables for which the equation is a true statement. So our definition of a solution is still the same. It's still the value for the variables that when substituted in makes the statement true. So number 1, which of the following order triples are solutions to the equation 2x minus y plus 3z equals 11? Justify your answer. Well, remember, answer is a solution if when substituted in makes the statement true. So here, if we had 2x minus y plus 3z equals 11, I'm going to substitute in 3 for x, 1 for y, and 2 for z, and see if I get a true statement. If it's a true statement, then yes, that point is a solution. It lies on that shape that's graphed. It's not a line. Okay, so here, 2 times 3 is 6, minus 1 plus 6 equals 11. 6 minus 1 is 5, 5 plus 6 is 11, and 11 equals 11. True statement, yay! So we have to say if it is, so we're going to say yes. 3, 1, 2 satisfies the equation. Cool. And if we take a look at B, we can see, we always want to write the original equation, 2x minus y plus 3z equals 11. What do you think? Go ahead, substitute those in. I got a false statement. This is false. So this is no, 1, 3, 2 does not make the equation true. Perfect. So now that we've talked about what satisfies and makes an equation true in 3 variables, same as with 2, same as with 1, makes the statement true, we're going to be looking at solving a system of 3 equations, meaning there's 3 unknowns. So the first thing that we're going to do is, of course, we are going to follow the steps. So A says, number the equations of the system 1, 2, and 3. Just like we've been doing before, but we're just numbering them 1 and 2. And this is going to keep our work really organized and help us solve. So it says solve for x, y, or z in any of the 3 equations. Well, looking at equation 1, x or z would be pretty efficient to isolate. In equation 2, x or y would be efficient to isolate. And in equation 3, y would be efficient to isolate. So it doesn't matter where you start, but we need to be organized, and let's do the same thing. So I'm going to solve for x in equation 1. So when I solve for x in equation 1, I'll write equation 1 here, x minus 2y plus z equals 0. I need to add 2y and subtract z, so I get x to equal 2y minus z. Okay. So now we're going to substitute the value we found in part A into the other 2 equations. And that's why it's important that we're numbering our equations, because we have to use all 3 to solve the system. So since we already used equation 1, we need to use equation 2 and 3. So equation 2 is x plus y plus 2z equals -1. I highly recommend crossing your z's because they otherwise will look like 2's. What are you doing? Substituting x value. Okay, so the x value is 2y minus z. Then we have plus y plus 2z equals -1. Combine like terms, 2y and y are 3y, negative z, and 2z gets you a positive 1z equals -1. And if we look at equation 3, the last equation we have not used yet, write the original equation, 3x plus y minus 2z equals 5. Remember, we're substituting in the value for x as 2y minus z. That's what we isolated in equation 1. Okay, so let's distribute. I get 6y minus 3z plus y minus 2z equals 5. 6y plus y gets me 7y. Negative 3z minus 2z gets me negative 5z is equal to 5. So a lot of times I like to call these 2-star and 3-star, so I know that I created a new system, and it's 2 equations with the same 2 unknowns, y and z. And now you know how to solve this. You can solve this with elimination, you can solve this with, I guess, graphing, but we know that that doesn't work out very well all the time. You could use elimination, you could use substitution. So use the 2 equation created in part B, I like to call it our star system, to make a new system and solve the system using substitution or elimination. Okay, so I'm going to rewrite my system over here. So 2-star is 3y plus z equals -1. And 3-star is 7y minus 5z equals 5. Taking a look here, I'm noticing that my z's are already opposite signs, so it's going to be pretty efficient if I want to use elimination. I just have to multiply my top equation by 5. And when I do that, I get 15y plus 5z equals -5. I'm just going to bring over my other equation, 7y minus 5z, additive inverses. And I'm going to show that I am adding that second one, putting parentheses around the whole thing, and showing addition with a circle. Bazzies. Okay, so 15y plus 7y is it 22 y's? is equal to a -5 plus 5 is going to get me a 0. Divide both sides by 22, and y is equal to 0. So I guess it doesn't matter if I added that right or not. Okay, so now we have our y value. What else is in the system? Z. So we can use either of these equations to solve for z. So I'll just use my 2 star. 3y plus z equals -1. I'm going to draw an arrow so whoever's reading my work can know what I'm doing. 3 times 0 plus z equals -1. 3 times 0 is 0. 0 plus z is just z, so z is equal to -1. So we're 2/3 of the way there. We already have 2 of our values, and we need our third. But you guys, there's no x in this system. Where's our x? Oh yeah, back to the original ones. So it says use the values you found in part C, so we found z and y, and substitute those values into one of the original equations and solve for the last variable you have left. So our last variable we have left is x, so I'm actually going to use equation 1 where I already have x isolated. X is equal to 2y minus z. So x is equal to 2 times 0 minus -1. Careful with your parentheses because of the negatives. So x is equal to 0 plus 1, so x is equal to 1. Now, what's the solution? We did all that work. Do not stop here. Our solution, remember, is the ordered triple, and it's going to go x, y, z. So this is going to be 1, 0, -1. And we could verify by substituting into the original equations, and all of them will be true, just like in number 1, part A and B. So what we could have done, we could have isolated any variable in any of the equations, and then as long as you substitute that value into the other 2 equations you haven't used yet. Sometimes when you start solving these systems and they get pretty messy and it takes a pretty long time investment, so you can always restart. You can always be like, wow, this is getting a little crazy. I bet there's a more efficient way, and maybe isolate a different variable from a different equation. Awesome. Okay. So what we're going to do is we're going to practice solving a system using our substitution by isolating one variable in one equation and substituting it into the other 2 to create a system of 2 equations with the same 2 unknowns, which you are great at solving. Okay, so first step. And if you want to have those steps next to you, keep this paper close to you so you can be like, okay, step A. What am I doing? Oh, okay, yeah, number the equations. So we have 1, 2, and 3. Okay, now, first thing we need to do is isolate one of the variables in one of the equations. We could do x or y in equation 1, we could do x in equation 2, or we could do y in equation 3. What do you want to do? Any ideas? Okay, let's isolate y in equation 1. And I'm just kind of listing out what I'm doing so I can follow my work if I wanted to recheck it later. So if I isolate y in equation 1, I'm going to add 3z to both sides and subtract x, and I will get y is equal to 3z minus x plus 3. Okay, now, what 2 equations have we not used yet? We haven't used 2 or 3. So we're going to substitute, I'm just going to put substitute y into equation 2 and 3. The other 2 we have not used yet. So equation 2 is x minus y plus 2z is equal to 2. Okay, so from here, remember this is the y value. The y value is 3z minus x plus 3. So x minus the y value plus 2z is equal to 2. From here, I'm going to distribute this negative. So I'll have x minus 3z plus x minus 3 plus 2z is equal to 2. Let's combine our like terms. Negative 3z plus 2z gets me negative z, x plus x. So I'll have 2x minus z. And I'm going to add 3 to both sides is equal to 5. And I'm going to call this my 2 star to make my star system. Okay. And I have not used equation 3 yet, so equation 3 is 3x plus y minus z is equal to 5. But remember, we found our y value to be 3z minus x plus 3. So 3x plus the y value minus z is equal to 5. We got this. Power through. Okay, so combining like terms, 3x minus x is going to get me 2x. 3z minus z is going to get me 2z. Subtract 3 from both sides is equal to 2. Lots of fun 2 stuff. The 2-step. Okay, so that's 3 stars. So now we have our new system. I like to call it our star system. So now we are going to solve the star system, which we have as 2x minus z equals 5 and 2x plus 2z is equal to 2. If you wanted to use elimination or substitution here, doing elimination, we could subtract our system. We could multiply the second equation by -1 and add the system, or we can multiply the top equation by 2 and add the system. I'm going to decide to multiply my second equation by -1 so I can add the system. So when I do that, what do we have? We're still going to have 2x minus z equals 5, and then we're going to have negative 2x minus 2z is equal to -2. From here, remember I'm adding, so I need parentheses around the entire second equation and an addition sign. Bam! That's gone. They're additive inverses by x. Negative z plus -2z is -3z. And 5 plus -2 gets me 3. Divide both sides by -3, and z is equal to -1. Hey, 1/3 of the way to our answer. Whew. Okay, so now in our star system, we have x and z. I have z, so I need to solve for x. So I'm going to use 2x minus z is equal to 5. And 2x minus -1 is equal to 5. 2x plus 1 is equal to 5. 2x subtract 1 from both sides is equal to 4. So x is equal to 2. Okay, so we have x, we have z. What are we missing? Y. Okay, well, we have to go back to one of our original equations, or hey, we already have y isolated there. So we know that y is equal to 3z minus x plus 3. So y is equal to 3 times -1 minus 2 plus 3. -3 minus 2 plus 3. Y is going to be equal to -2, because -3 plus 3 cancel out. Final step. Write your answer as an ordered pair and give it some flair. Zoom out there for you. Cool, so our final step, x, y, z, 2, -2, -1. And you can verify that into each original equation, and they will make a true statement. Great work. Okay, many mathematicians, it is your turn. Go ahead. You're going to be solving equation system number 4. Remember, isolate one variable in one of the equations and substitute into the other 2 to make your new system of 2 equations with the same 2 unknowns. Pause the video and restart when you're ready to go over the problem. Okay, let's see how you did. So I decided when solving this problem to solve for x in equation 1. So I had x equals -y minus z plus 1. And then the two equations I haven't used yet were 2 and 3. So I substituted that value of x for x in equation 2 and x in equation 3, and I simplified to write these with the y's and the z's and the constant terms lined up. From there, I solved my star system. I chose substitution, and I got my z value to be 0, my y value to be -2, and then I went back to my original equation to solve for x to get my final answer of 3, -2, 0, written as an ordered triple. Great job. What I want to show you, mini mathematicians, really quickly is that you don't have to do substitution in the very beginning. Remember what your goal is. Your goal is to write two equations, the same two unknowns, using all three equations. So something we could have done is used elimination. So I'm going to show you the same problems but solved with elimination, and this is also in the worked out notes linked on your calendar. So to solve with elimination, I'm going to use all three equations to eliminate the same variable, working with two equations at a time. So I decided to eliminate y by adding equations 1 and 2. I still needed to use equation 3 because you have to use all three of them. And I noticed equation 3, and I still needed to eliminate y because you want the same two variables left in your star system. I noticed 3 has an additive inverse with y with equation 2. So when I added equation 3 and equation 2, I got an equation that's x and z. So now I can have two equations, the same two unknowns, my star system, and I can solve that with elimination or substitution. And I can solve for x and z and then go back to the original, one of the original equations to solve for the last variable and write my answer as an ordered triple. And I got the same answer as I would with just isolating one and using substitution to create my star system. So I'll show you that one more time with the second problem with system 4. So system 4, I decided I wanted to eliminate z. So I noticed equation 1 and 2, the z's were additive inverses, so I added those together to make one equation with x and y, so that's one of my star equations. I still needed to use equation 3, and I still needed to eliminate z. So I noticed equation 1 had an opposite sign for z, so I just multiplied equation 1 by 3 and then added to equation 3 to notice that z's canceled out and I had a new equation with just x and y. So now I have my star system, two equations with the same two variables, and I solved. And then once I solved for x and for y in my star system, I used an original equation to solve for the last variable I needed, z, and wrote my answer as an ordered triple, and of course you could verify. So I just want to give you that option since a lot of you really enjoy elimination to solve. Okay, so just like solving systems, we of course have real world word problems that we can solve with these three variables, which means we need three equations. In any system, if you have two variables, you need at least two equations to be able to solve. If you have two unknown variables and only one equation, it's impossible to solve. You don't have enough information. Here, since we're going to have three unknowns, of course, we're going to have three equations. So let's get started. Michael has 11.25 in nickels, dimes, and quarters. He has 3 times as many nickels as dimes and 5 more quarters than dimes. How many of each coin does he have? Define 3 variables and use a system of equations to find your solution. Show all your work and write your answer in a complete sentence. Well, let's take a look at what our unknowns are here. Let's say n is equal to the number of nickels D is equal to the number of dimes, and Q is equal to the number of quarters. Okay, let's think about from the word problem what type of equations we have. Well, it says he has 3 times as many nickels as dimes. So 3 times as many nickels as dimes. Which one does he have more of? He has more nickels and less dimes. So that means if I want to set them equal to each other, I have to multiply the number of dimes by 3. So n is equal to 3 times d. The next part of the word problem says 5 more quarters than dimes. So which one does he have more of? He has more quarters than dimes. If I wanted them to be equal to each other, I'd have to add 5 to make them equal to each other. So we know that Q is equal to D plus 5. I have more quarters, so to set them equal to each other, I need to add 5 to the smaller amount. But guys, that's only 2 equations. Where do they tell us about a third equation? Oh, the total money. Total money. So 1 nickel, 0.5. I wish a nickel was worth 50 cents. I'd change all my money into nickels and be rich. Okay, so multiply your money by 10 that way, huh? So the value of a nickel times the number of nickels plus the value of a dime times the number of dimes plus the value of a quarter times the number of quarters is equal to the total amount of money, which in this case is $11.25. Awesome. So now that we have our 3 equations and our 3 unknowns, our goal is to create 2 equations with the same 2 unknowns to eventually make 1 equation with just 1 unknown. But you might notice something. Do you see how this n is isolated and is in terms of d, and this q is isolated and also in terms of d? If we substitute in n in our total money equation and q in our total money equation, we're going to have 1 equation with 1 unknown. So it's really important to not be a math robot. Boop, beep, bop, bop, beep, boop, boop. Think about what your end goal is. Your end goal is to create 1 equation with 1 unknown, because that's how you know how to solve. So that's what we're going to do. We're going to substitute in n for total money and q for total money and solve that equation. Okay, so 0.05n plus 0.10d plus 0.25q is equal to 11.25. And your n value is 3d. So 0.05 times 3d plus 0.10d plus 0.25. And your q value is d plus 5 is equal to 11.25. You could have cleared your decimals if you wanted before this step, but I just didn't, which is fine. So from here, you could always clear your decimals if you wanted to. And when we multiply, we're going to get 0.15d plus 0.10d plus 0.25d plus 1.25 is equal to 11.25. Okay, so from here, let's combine our like terms, 15, 10 cents, and 25 cents. So that would get you 50 cents, because 15 cents and 10 cents get 25 cents, and 25 cents plus another 25 cents is 50 cents. I like thinking about decimals like money, because who doesn't like thinking about money sometimes? Okay. So from here, I need to subtract $1.25 from each side. So that would get you $10. And divide 50 cents on each side. 2 groups of 50 cents makes $1. So to make $10, we would have D is equal to 20. So we have 20 dimes. So from here, what do we still need to know? We need to figure out the nickels. We know nickels is equal to 3 times D, so nickels is 3 times 20. So 60 nickels. And our quarters, Q equals D plus 5. Q is equal to 20 plus 5. So Q is 25 quarters, each worth 25 cents. And before I start writing my answer, I want to double check that this will add up to the right amount of money. So I can do a little verifying. So nickels, I'd have 60 of them times 5 cents each would get me $3. And dimes, I have 20 of them times 10 cents gets me $2. And quarters, 25 quarters at 25 cents a piece gets me $6.25. Add them all up. Let's see. 6, 7, 8, 9, 10, 11. Yay! 11.25. Whoop, whoop, whoop. Okay, let's write our answer in a beautiful, complete sentence, since we have plenty of room down here. Michael has 60 nickels. I like going from like least amount of money to most. So like nickels are worth less. So 60 nickels, 20 dimes, and 25 quarters. And you can write in any order you want. And then I like to underline these. Aww. Excellent job, mini mathematicians. Variables, 3 variables with 3 systems is not, sorry, I misspoke. 3 variables with 3 equations in one system is not an easy feat to solve, but you guys are doing a great job. Remember to persevere and be resilient. If you notice your solving process is getting a little icky, just start over. There is nothing you can't solve. You're doing a great job.